My name is David Paczona, and I'm a scientific project assistant at the Chair of Energy Networking Technologies at the Montanuniversität Leoben. And in the meantime, you hopefully can see my screen.
For me, it's still black.
Okay, maybe a moment.
Yes, now it's here.
Okay, perfect. So, and I will give you an overview today about the project first, which is about the fully integrated reversible solid oxide cell system. As the name says, it's a reversible solid oxide cell, which means a high temperature electrochemical cell that can operate in fuel cell mode and in electrolysis cell mode. In my presentation, I will give you an overview about the project at first, and then I will talk about the motivation for looking at such an RSOC system. Then I will talk about the system development process and the investigation of application scenarios. And I hope I will be able to make the point of how it is all connected with digital twins. So the project first consists of 4 members, where 3 of them are research institutes, the Forschung Burgenland GmbH, the Energy Institute of the Johannes Kepler University Linz, and the Chair of Energy Networking Technologies of the Montanuniversität Leoben. And we have 1 industry partner in our project, the AVL List GmbH. The project started almost 2 years ago, and it will be continuing for almost another 2 years. In the project, we have 4 main topics that we are dealing with. We are developing a RSOC system, which is mainly the task of the industrial partner AVL. This system will be then integrated in a living lab environment where it will be tested for longer time. And the task of Montanuniversität Leoben is mostly the investigation of the application scenarios of the system, where we are looking at how to combine such a RSOC system with a proper hydrogen storage, and how it can act in a system consisting of renewable production on one side and consumption of electricity, hydrogen, and heat on the side of industries or in the building sector. And it all can interact with electricity and gas grid. And as a 4th topic in the project, we have an economical impact assessment of the RSOC system. So why do we look at an RSOC system at all? Why is it interesting for us and for the Chair of Energy Networking Technologies? The renewable production with photovoltaic and wind turbines needs storages on different levels, which was already shown in many publications. Like, for example, in this graph, we can see the spectrum of the difference between demand and production. One can see that this spectrum of the difference of demand and production has a big component, a big yearly component, as well as a very big daily, half-daily, and weekly component, additional to an overall DC component, which means a lack of energy in the future system, which has to be covered by measures of increasing renewable production or increasing efficiency. And the RSOC system, as it combines electrolysis and fuel cell in one system, can provide the short-term storages, as it can be coupled with the hydrogen storage easily in industrial and in building applications. And the long-term seasonal storages can be also dealt with if we couple the system with the gas grid. So this is possible for large systems acting on a grid scale. So coming back to what we do in the project, the RSOC system development, which is mostly done by our industry partner, AVL. They are trying to find the proper flowsheet design for that system by employing a model, a virtual representation of this system. Let's call it digital twin, which is built on manufacturer's data of all the components in the system, of the main components in the system, like the electrochemical cell stack. The smaller components are calculated with physical principles and semi-empirically. By having such a virtual representation, the design can be done to a very accurate level already in this virtual environment. The components can be selected that should fit to the real prototype, and already controller setups can be done so that the system running then in a prototype state is less likely to fail, and it's less likely that component damage will happen. And it's not only that this is happening once during this process, and then we suggest the AVL suggests a system that is built, but the system setup is also done in parts. Like we have the gas side of the system and the stack, which can be run separately from the electrical control units. And by testing this separate gas system, we can already get some measurement data from the test benches and integrate it back into the virtual representation, which in return can give us better results for the parameters for the controller setups. As it's probably quite obvious, this model, this representation or digital twin of this prototype has to be quite accurate and well fitted to the real components used in the system. And the chair of energy networking technologies, the Montanuniversität Leoben, is investigating the system on a little bit different level, which will be the topic of the next slides. We are trying to look at the application scenarios. We can visualize such an application of this RSOC system with a hydrogen storage, like it's shown here, interacting with renewable production on one side and industries on the other, and exchanging electricity and natural gas or hydrogen with a grid infrastructure. This renewable production on the left side for the investigation of the application scenario can be provided as time series for wind turbine production or photovoltaic production for a specific given location, so that it really reflects the place where the system will be set up. One can see that such renewable production indeed has very high fluctuations. So the system should be able to deal with these fluctuations. And on the other side, we also have some consumer which do not have constant consumption over the time, but also have some time-dependent fluctuations in their consumption profiles, here, for example, for electricity. And we investigate some industry groups with synthetic time series for the load profiles, like for iron and steel, pulp and paper, cement, chemical and food industries. We would like to do it. And in this setup of time series that the system shall interact with, we need a good model of a good representation of our RSOC system, which behaves like the real system, which can deal with time-resolved calculation and has proper path load characteristics, and different than the system developed for the different than the prototype system. We are not just looking at one configuration of the flow sheet, how it could look like, but we want to investigate different changes that we can make in future to improve this system, to improve the design. Coming from the application side, seeing what is needed, what volatility, what changes do we have in this application. So what should the system look like? What's important that it features? So our aim is to rate in such a way operation strategies and to rate the system design and to give quantity, to give the effect of some measures with numbers to describe it quantitatively. If we have now a closer look at our model that we use for the RSOC system, here I have given two different flowsheet configurations for the RSOC system, where the left side indicates the fuel feed side of the stack. Here in the middle we have the stack, and on the right side we have the air provided for the reaction. And one can play around with different configurations. For the RSOC system, it's always advantageous to have a recirculation of the exhaust fuel. This means that also a part of the hydrogen is already used. We want to recirculate a part of it to be able to have a higher fuel utilization on system basis, because the stack is limited in that matters. And here was done only a small change to this configuration. We have the recirculation of the exhaust fuel gas of the stack on this side, and we can add to that a condenser to cool down the recirculated gas, which is advantageous in that aspect that steam is removed. So the hydrogen concentration of the feed gas to the stack is higher. It's not lowered so much by the recirculation. And additionally, the condenser in the recirculation might be necessary for a recirculation system that's not working with an ejector, but with a fan. Then we have to reach low temperatures not to that the fan can deal with. So, and the state that we at the moment at is that we looked at different configurations. We have a model that we have different models for different configurations, and we calculated some maps, how the behavior, how the efficiency of the system changes with changed parameters of fuel utilization and of recirculation rate in this case. And this was also done for two different application scenarios that we can see here. The energy sector scenario means that we do not have a thermal interaction with industry or households. That means here no thermal interaction and we only have electrical interaction with the surroundings. which means all the energy consumed by the system in electrolysis mode has to be provided electrically, and in fuel cell mode, all the waste heat produced in the system is lost to environment. So in this case, electrolysis mode can reach 78% of efficiency, and the fuel cell mode can reach up to 68%. And in the industrial scenario, we calculated the use of energy on a exergy basis. So we rated the thermal energy as exergy and compared and calculated the efficiency, which increased the efficiency in electrolysis cell operation to 88%. So almost, basically 10% increase by using waste heat of the industry, mostly for evaporation of the feed water. And in fuel cell mode, the efficiency in industrial scenario, which means that we can use the thermal waste heat of the system, was increased by 8%. So, and what's the aim for in the project for the next steps? We are trying to investigate now to put this system model that we calculated this efficiency maps with into the time series of our application scenario. And this all is then more or less the digital twin of the application, which is how the system would behave like if we would have it already like that and we would put it into the industry. And then from this we can say what is the desired behavior of the system. We can propose a different system design and identify maybe bottlenecks and crucial parameters that are important to improve the performance. And with this knowledge, we can go back to the circle of the system development that's done by our industrial partner and change the system design. So in the next step, the aim is in the project to propose the next generation, how the system can be improved like, and to verify the zeros version of the system. And that's the end of my presentation, and I'm looking forward to your questions on RSOC systems and connected digital twins. Thank you.
Thank you, David, for this very detailed presentation of your project. I was wondering if I understood it correctly, you're not using the same model for the flowsheet simulation and for the time simulation, right?
Yes, because the thing is that AVL uses here a pretty detailed model. It's calculating in real time, basically. So I don't want to calculate 1 year in real time on my computer. That's why I have to simplify this model. I can use their model to validate mine. That's how we do it. But I cannot use their model directly.
All right. Well, this is like a challenge that you're often faced with in digital twin design, that you have sort of various models for the same thing, just on different timescales or levels of detail.
Yeah.
So I'm really looking forward to hear what solutions you're coming up with for that. Though I think this is like better suited for the later parts of the annex, when we are like talking about the methods more specifically. Mm-hmm. Are there any questions to David? Well, if not, then...
Oh, yeah, yes, I have a quick question, sorry.
Oh, yeah, sure.
This is Arno. Just to understand maybe less on the project itself, more on the vision. with that RSOC, do you see it being centralized at specific industrial sites? So basically distributed, or like one centralized place where you'll have thousands of them and redistribute the energy, heat, or hydrogen to the different industrial places?
We want to investigate both cases.
Okay.
So we want to find out what's the best design of the system for the case of a centralized plant, which has maybe several megawatt of power, and the other case of industrial application where we are talking about several hundred of kilowatt power, which has different demand, different requirements for the system design.
And have you already engaged with the industrial sites to understand how they would manage that? Because if you want to leverage the hydrogen or heat, you need to buy it or sell it. So there is an additional logistic or contractual aspect to it that can play a major role, because some companies are going to tell you, I want your heat, but I will never pay for it. Some are going to tell you, I want to give you my heat for free, or going to sell it. So that can completely change your model, basically. So have you heard back from some people on how they would use that type of tool?
I think we are not at the state where people are aware of how they could use it, and industries are not fully aware of it either. And we are trying to propose different ideas and find out what could work, how could the system be economically. Maybe we even need we definitely need a different framework of our government, of our rules, of our legislative.
That's one of the challenges that we saw in several places, including here in Canada, where several people have that type of idea, but currently the legislation doesn't even allow them to do that. So it's a challenge. But I saw a project that was very interesting, kind of not exactly the same type of technology, but something related. And the way they were able to promote it was for remote places. We have a lot of them in Canada, and basically having a small unit, but to give access to people very, very far away, access to, leveraging both the wind, photovoltaic, sometimes marine, or like river energy, depending on the different levels, packaging it and provide them with electricity and or hydrogen storage. So it's a smaller, small community level. So basically for a couple of houses of production and uses. And in that way, they were able to actually develop it and make a prototype and deploy it. This way, you get rid of all of the legislation and stuff like that, because they're not connected to the grid, so they don't have that capability. There is less a challenge of commercial aspect, because they're currently producing all of the electricity from fuel that they have to buy at huge price. So that may be one way to think about it. Maybe that's less relevant in some areas in Europe, but there are some places around the world where they would benefit from that. But that means a smaller scale system. Just an idea.
What I heard of our energy providers that it's interesting also for them is if we make the system blackout safe. I mean that it can start up without external energy. Yeah. Then such applications could also be interesting. And the island kind of systems, I'm not sure where we need it, but at the moment also electrochemical storages, batteries are quite cheap. So for households, it might be not so competitive. But in the future, who knows where it's going? The RSOC system is at the beginning of its development stage, I would say, and the prices are only very likely to go down in the future.
But the battery cost will also go down, so it's going to be chicken and egg. Maybe the difference is going to be that batteries still have high chemical content, so some challenge with the environment, and some rare earth minerals that you probably won't have in terms of challenges. So
But
located
I'm
differently.
pretty sure that batteries will stay for all short time
Yes.
storage.
You won't use battery for 7 days storage.
Yeah, but for long-term or seasonal storages, we definitely need something else that is coupling to gas system. And then it would be good if you can use the system for both. Then it's maybe cheaper.
And that's cases we heard for mines in north of Canada, where you have basically 3-4 months a year, you have a lot of wind and solar, but for like 6 months you have none. So you need those long-term storage. And that battery when it's minus 40 degrees outside, batteries doesn't necessarily work as we hope them to do. While your system might be more efficient. So yeah, there's different applications, but that's a very interesting idea.